Hello, everyone. So let's start our third computational prac. This week, we're looking at detector efficiency and peak fitting. So I already shared with you the link to the GitHub where all the material and all the links that you will need are already on there. So you've used GitHub already for the last pracs, and you have all the files that are included here at the top. The .root files are the data files that you're going to work with. Introduction PDF are the slides that I'm going to show. The README file is always all the instructions that are at the bottom here. So you can just scroll and read them there. So first, the links to the first practicals 1 and 2 are already available on YouTube, so you can always refer to that. Here, we're going to build on that. So on your machines, you should already have root running and the Ubuntu subsystem, of course. So what I didn't force you to install already is Greasy sort, the code based in root that is written by the gamma ray spectroscopy group at Triumph, where I did my PhD, and which is the code that I used to do my analysis for my PhD, and now for the Tigress data that we have in the group. So we'll go over this, and it's also the code that I want you to use because it is very simple to get very good data, very good peak fitting. So I'm just going through those notes first to make sure you know that they are there. Okay, so first, to download a repository, which is a folder here on GitHub, you can simply go at the top here, and you can download everything as a zip file, or you can use the link and just clone everything. So we haven't installed the Git yet, but you will to install the Greasy sort. So you will use that command over here. And the rest is already in the slides. So I'm going to pull up my slides here. So this practical is detector efficiency and peak fitting. What you need to do for this prac is the detection efficiency calibration of real germanium detector arrays from around the world. So this is what you'll do mostly tomorrow. You will install the sorting code and analysis code called Greasy sort. You will fit the gamma ray photo peaks using the Greasy sort code. You will edit and run the root efficiency script that is available on our GitHub. And you will get marks based on your submission of your fitted peaks, your edited root efficiency script, and your own efficiency curve. So in order to do that, you need to know a few things, and this is what we will go over today. So what you need to know in order to do all of this, first, you need to know how semiconductors detectors work, how to determine the detection efficiency of many types of detectors, but today about semiconductor detectors, how to find nuclear information on any type of nuclear property of any type of nucleus, how to compile a code, specifically in C++ and in root, how to fit the peaks with Greasy sort, which is exactly what you have to do tomorrow, and how to run a script in root or Greasy sort. It is the same way, so in root and Greasy sort. So this is what I will go over with you today so that you know how to do everything you need to know in order to do those points over here. And what we expect you to submit at the end, I'm just saying it again so you have it in mind. We need to see your fitted peaks. You will need to take screenshots of the peaks and their fits. We want to see what you edited in the root efficiency script, and we want to see your fitted efficiency curve. But first, let's talk about real germanium detector arrays. We will work with several data files from several detectors. So first, I introduced to you the Griffin Array, which is at the Triumph Laboratory in Vancouver, Canada, where I was living for 8 years before I moved here in Cape Town. It is the array that I used for my PhD. My PhD data was collected using this array, so that is the array that I'm the most familiar with. And it is made of 64 germanium crystals. The next array that we have is Kenzo over here. Kenzo, Kenzo just finished his PhD using mini-ball data from CERN. So here we have a different type of array, but it is made of 24 germanium crystals. The next, we have the soccer ball at Itemba Labs here in Cape Town. And you can see it is, again, slightly different configuration. The detectors are not placed in the same position, but it is still using crystals of germanium. In this case, we have 52 crystals. And our fourth array that we will look at is the Tigris Array, also at Triumph in Canada. So here we have a picture of when the UWC group and Sifiso from Unizulu visited in 2018, which is when I met the whole group. So here you see this is the array while it is open. So you have one hemisphere here and another one here, and the whole group is sitting right in the center of the detectors. And all together we have 48 crystals. Zoom is always in the way, so 48 crystals now I can see. So you can see everything is a little bit different, but always germanium crystals. So let's look a little bit more in detail how those different detectors are arranged, or the different configurations. So starting with the most simple type is the Clover type detector. So you can see here we have 4 crystals that are arranged in a clover shape, a lucky clover. And this is why we call this type of detector a Clover detector. Each physical detector contains 4 germanium crystals, which means that even if we have 64 crystals in the array, we actually have 16 physical detectors that are like packed together. And this is the simplest type of detector that we're going to discuss. It is not segmented. So a segmented detector, the Tigress detectors, are very similar. It is, again, a clover, which means there are 4 germanium crystals per physical detector. And what is different with the Tigress detector is they are segmented. And in the Tigress, it is 8-fold, which means they are each crystal is segmented using wires in 8 different parts. So you can see the lines here are the actual wires where the charge that are created in the detector will be attracted to a specific wire that is closest to them, and that will give us a better indication of where the radiation actually happened. So that gives us better angular distribution or physical distribution or position. And yeah, this is what we have at Tigress. So from the outside in real life, this is what it looks like. So the 4 crystals are in the aluminum casing over here. And germanium crystals, to function properly, needs to be kept at liquid nitrogen temperatures. So we have a big reservoir or dewar over here. The electronics are all in the part over here. They are not cooled down, but the cold finger, like we like to call it, is the part that bring the cold from the liquid nitrogen directly to the germanium crystals. Our next array, soccer ball, is a combination of clovers that are segmented and not segmented. So for the data that we are looking at, there were 4 clovers that were segmented that actually are called Tigress detectors because they are the exact same, and 9 clovers that are not segmented. So they are similar to the Griffin one. Different companies do different detectors, but it is a very similar design of the clover, just 4 crystals per detector, and either it is segmented or not segmented. Finally, we have a different type of detector, which is the triple cluster. So each crystal that we have here has its own aluminum capsule, which is then joined by two other crystals. So you have three crystals per detector, per physical detector. And this is why they're called triple cluster detectors. And the electronics is very similar to the Clovers, of course. So we have the liquid nitrogen reservoir or dewar, and all the electronics, the preamplifiers and any high voltage filters, any electronics is kept under the cover here. So physically, this is what the detectors look like. And we're all looking at germanium crystals. And most specifically, we call them the closed and coaxial right cylinder crystals. So as you can see over here, this is a cylinder, and there is a hole in the center. So we call it a coaxial for that reason. There is a hole in the center, but it doesn't go through all the end, which is why it is close-ended. So again, for the Tigris detector is the same thing. It starts as a cylinder that with a hole that doesn't go all the way through. And depending on the design, it might be chopped off or tapered, like the right word is. It is shaped to fit more closely, to be able to fit more detectors in the array. So we call that closed pack. It is the reason that they're not perfectly squared or perfectly round. So I'm just telling you all of this because I think it is interesting information since we're going to look at data coming from those detectors. So now we want to know how the germanium works, of course. So germanium is a semiconductor material, and I have no idea if you had physical solid state physics already. So you're in third year. Can anybody tell me in the chat or speak up, do you have any idea what semiconductors are? Any solid state physics was done already? Guys?
They typed on the chat.
I don't, what did they say? I can't see the
Okay,
window.
they said we do solid state next semester. We have not done
Okay.
it.
Okay, perfect. Thank you. I can't pull up the window. Okay, so that's interesting. So I'll give you a very short introduction. I have no intention on doing a solid state lecture right now. So this will be a quick introduction, and then when you do it next term, you'll already have an idea and you've already looked at data coming from a semiconductor. So hopefully you think that's fun. I think that's exciting. So how do semiconductor detectors work? Here we have a crystal, and we have free charges, of course, going around. And there is a region where there is an imbalance of charge that we call depletion zone, and without bias, which means without applying a high voltage on it. So the first step to create a semiconductor detectors is to use an external field, a high voltage, to create an area that is depleted of charge carriers. So we want to separate all the electrons and the holes. So yeah, that will make more sense once you do solid state physics. So the N, we will use those letters N and P to describe the type of the detectors. N means there is an abundance of negative charges. So this is the side where there will be more electron. P is the positive side where there is more positive charges. This is where we have the holes. So when we apply a high voltage, we can increase the size of this depletion zone, or the area where there are no more free charges going around. We use an external field to do that. The next step, of course, is radiation that comes into our crystal, into our detector, and it interacts with the crystal and produces electron-hole pairs. Have you seen that already? How do photon interact with matter? Is that something that you've seen in any lecture, any class? And Daphne, you can tell me what the chat says, please.
Yes, I will do. I'm waiting for the message.
Okay.
Guys, please answer the question.
Have you ever seen matter and photon interaction? That could probably be in an E&M course or nuclear physics course, like you're doing right now.
So they say they know photoelectric effect.
Yes. Compton scattering, pair production.
We did that in the last prac, yes?
Yes, of course. Okay, so if you remember from the last prac, that will be our starting point, and hopefully you might see that in solid state, maybe. Anyway, this is how photon interacts with matter. So this plot summarizes everything. On the x-axis, we have the energy of the photon, or in our case, we're interested in gamma rays. And on the y-axis, we have the Z of the absorber of the material. So you can see there are three ways that photons can interact with matter. The photoelectric effect, which is more dominant at low energy and higher Z. In the center around 1 MeV, the dominant effect is the Compton effect. So this is Compton scattering that I would expect Prof. Nico to have said a word about. So Compton is the gamma ray scatters. So it interacts with the material and then leaves some energy and continues in another direction with a gamma ray of another energy. So this needs quite some energy to be more dominant. And finally, with higher energy, we have pair production. So a gamma ray that enters the crystals can stop and emit a pair of electron-positron, so antiparticle that equal the mass, the energy of the gamma ray. So the minimum energy that a gamma ray needs to do pair production is twice the mass of the electron, of course. So 511 keV times 2 is the minimum energy of the gamma ray. So those are the three ways that the gamma rays can interact with our detector. And I'm not going into the calculations, but we can see what is the angle that's, for example, in quantum scattering, at what angle the gamma ray can scatter. The photoelectric effect, I assume we can calculate that, and pair production as well. So we have physics means and maths means to calculate how those three processes happen. So this is the second step, of course. Those interactions happen in our detector. And finally, with the interaction, the electron-hole pairs that are produced in the crystal by the interactions are in that external field that we applied. And therefore, the electron and the holes drift towards the electrodes that we called contacts. And then we extract the electric pulse, which is amplified and processed, just like we did with the sodium iodide prac in the last weeks. So here we have a look at our coaxial germanium crystals. So this is the type of crystal that we have in the 4 arrays that we are interested in today. And we have our hole in the center, and we have the outside of the the cylinder. So those are the two places that we can apply our external field. So depending if we apply the positive and the negative in the center or the outside, the electron and holes will drift towards a different surface. So let me take, for example, the N-type coaxial, which most detectors these days are N-type, which means we apply the positive in the center, in the hole that we drilled there, and that becomes the N contact. And on the outside of the crystal is the P contact, which means that the electrons will drift from the outside of the crystal to the center, and the holes will drift to the outside. So wherever the interaction happens within the crystal, the electrons will always drift towards the center, and this is where we collect our electrons to get our electric pulse. This could be a full solid state physics lecture and course. So this is not what I want to do today, but I wanted you to have an idea how things work. So the interesting thing that we can do now that we know a little bit is to compare with the scintillators. But first, here are all the references for those figures. And if you want to know more about those detectors specifically applied to gamma ray spectroscopy, those are my 3 favorite textbooks where you can find all the information that you need, really. So Crane is my absolute Bible since undergrad. It's been following me. Knoll and Leo are a little bit more focused on detectors. So there is a lot of information there that you can find. Now I want to make the transition from the scintillators, the sodium iodide that we worked with for the last 2 pracs that you're familiar with, and you've played with the software, you know what peaks look like. So now we can move on that and work with the germanium. But first, what is the difference between those two? So first, we need to talk about band structure, electron band structure, and different types of material, because this is really the strength of the semiconductor detectors. They are very powerful, and this is the reason why. So first, you know about, let's start with the metal. You know metals, where you have a valence band and a conduction band that's overlay. So electrons are free to move around. They are very good conductors. They are metals. On the other side, we have an insulator where the valence band and the conduction band are separated. There is quite a big gap between the valence and the conduction, so that the electrons cannot jump to the conduction band. So there is no electrons moving around, there is no conduction, and we call that an insulator. So in the center, a semiconductor has a valence and a conduction band that not quite overlap, but are not quite separated. So there's a very small energy gap, such that if radiation comes in or an external source of energy is applied, those electrons can quite easily jump to the conduction band. So they are not conductor as is, but they can easily be made to jump those free electrons to the conduction band. And putting values for that energy gap really tells us a lot about why semiconductors are so powerful, why they have different strength, I should say, than scintillators. So here I'm comparing values for the sodium iodide that you are already familiar with, germanium, which you will be familiar with today and tomorrow, and any day after that. And I also added silicon, which is a detector that we also use within our detector array. So those are the 3 main types of detector that we use. So sodium iodide is a scintillator, and there's also lots of plastic scintillators that are very cheap and very effective at detecting radiation. So we also use that. So first, we need to categorize them. So we were using a scintillator before, and today we will be looking at data coming from a semiconductor. A big difference for germanium is we need to cool it down at a liquid nitrogen temperature. So liquid nitrogen is around 70 degree Kelvin, which is very, very cold, of course. And once we put it in the detector, of course, it warms up a little, but the detector is in the big reservoir. So for the detectors that we use, the reservoir usually keeps 8 hours of liquid nitrogen, or 12 hours, but we fill it at Triumph every 8 hours to make sure that if problems happen, we have plenty of time to fix it. So this is crucial to use a germanium detector, but not for silicon and sodium iodide. But this is a small price to pay for the quality of the data that we're interested in. The density, of course, is very important. It will affect how much radiation interacts with the crystal. So if, like we saw for, let me go back here. You see that the different interaction depends, or the probability of interaction depends on the Z of the material, of the proton number of the material. So here the density is very important. The more dense the material is, the more the radiation will interact with it. So this will increase our detector efficiency if we catch more of the radiation. Here, the band gap energy is the energy here, the band gap between the valence and the conduction band. So first, let's go straight to germanium, 2.9 electron volts. It is very, very small. And this is where the magic happens. If you compare with silicon, it is just a little bit higher, not bad at all. But if we look at scintillators, we are talking about a totally different game. And this is why scintillators do not produce radiation, or they do not detect radiation in the same way as semiconductors do. So remember, with the sodium iodide, it scintillates. The electron levels are excited, and they excited very quickly, and they phosphorus, and they emit photons that we capture with the photomultiplier tube, the PMT, which is then multiplied. So this is a different game with semiconductors, as we've just seen. So the band gap energy tells you what can be considered as a semiconductor and what cannot. This translates in the measurement of how good not how good a detector is, or just how good the resolution is. Depending on what you want to measure, this might be a deal breaker. So because of our very, very small band energy in germanium, we can expect a resolution of 2 kV at the cobalt 60 peak. Remember, you've worked with the 1332 from cobalt 60, and we have a much smaller resolution than what you've had with the sodium iodide. So this is what the two detector look like overlaid. So the sodium iodide is what you saw last week. So you are probably familiar with those shapes now, but on top of it is the germanium data. So they are both good. I don't mean to say one is not good, but if you are looking into detailed work, you need something like germanium. If you want to, if you're more interested in the detection efficiency, of course, the scintillators will have a higher detection efficiency. However, the resolution will be not as good. So depending on what you want to measure, you want to choose carefully your detector, either a scintillator, a semiconductor, or any other type of detector. And in most of the experiments, in most of the arrays that we're looking at, we actually use a combination of detectors. So we use, today I'm focusing on the germanium detectors, but we never just use germanium. There's always, in the case of nuclear reactions or Coulomb excitations, which is mostly what Prof. Nico and the group does at UWC, Coulomb excitation, we always use a silicon and a germanium. For my PhD, which was beta decay spectroscopy with Griffin, we have, of course, the germanium, but also a scintillator to detect the beta particles that come with the beta decay. We don't care, in the case of beta decay, we don't care about the energy of the beta. We just want to know that it happened. So a cheap plastic scintillator can perfectly do this job. However, when we want to look into detailed gamma ray spectroscopy, we will need to look with a germanium. Okay. Please let me know if there are any questions, of course. And today and tomorrow, of course, anytime you can always ask question. But I think this material right now is important just to capture what we've done so far in the lab with the sodium iodide and what is different with what we're doing today. And this is what it looks like. Visually, this is the difference between the two. So next, what we're interested in this lab is we want to determine the detection efficiency of our detectors. So we use our fancy germanium detector or sodium iodide detector, any type of detector, to detect the gamma rays coming from our radioactive source. So what is the actual detection efficiency? It is simply the ratio of how many gamma rays we detected with our detector over the number of gamma rays that were emitted by the source. So it should be a simple number, and I hope that this, by intuition, you could guess that. And here I'm talking about the absolute efficiency because I want to know exactly how many gamma rays were emitted by the source. And of course, we divide how many gamma rays we saw by that absolute number of gamma rays that could have been detected. So it is the ratio of what we saw over what could have been seen. So how do we get those two numbers? First, the number of gamma rays detected is simply the area of the photopeak. So we've been calling them peaks, but more precisely, they are photopeaks because they are coming from photons, from high energy photons, gamma rays. In the software that we were using in the lab for the multi-channel analyzer, you could find a region of interest and you could find a rough centroid and the integral of all the counts that were in that region of interest. Today, we're going a step further. We're going to fit that peak to get a more precise number of counts in that peak, a number of gamma rays that were actually detected. Then in the denominator at the bottom, we have the product of three quantities. So first, we want to know how many gamma rays were emitted. So we need to know the activity of the source times the collection time. So the activity of the source will be something in becquerel, which is the number of decays per second. If we multiply that by time in seconds that we were actually measuring, that gives us the number of decays. Simple as that. The only thing that we need to add in there is the absolute intensity of the gamma ray itself. So unless for each decay, a gamma ray of one energy comes out, then that is 100% absolute intensity. But if we have two gamma rays or more gamma rays, we have to know what is the fraction of the time that we see that gamma ray. So if we have, let's say, 100 decays of our source, of our isotope of interest, how many times is a gamma ray of that energy emitted? So for radiation sources, those numbers are very well known and are in databases. And I will show you next how to find the information from those databases, because that is the information that we need to calculate our ratio for the efficiency. So we do this at several energies. For example, if we think of the cobalt 60, remember it had 2 peaks. We look at the 1173 keV peak. We fit the peak, see how many counts there are, and divide that by the intensity of that transition, divided by the activity of the source and the collection time. Then we go to a different energy at 1332 keV, and we do the same calculation. We get the number of counts in that peak, we divide by the intensity of that peak. That gives us a bunch of data points that we can then fit all together. So this is the equation for the efficiency as a function of the energy of the gamma ray, which is 10 to the exponent of all this. So the parameters that we are interested in extracting today are the P not P1, P2, P3. And the rest is all a log of the energy, log square of the energy, and divided by the energy squared. Of course, this is already in the code. You don't have to worry about it. You just have to understand what the code is doing. So I'm telling you, this is what the code is doing, and you will have to look in the code to check how it is doing it. This is how we calculate the absolute efficiency of the detector. However, for many types of experiments, we do not need actually the absolute efficiency of the detector. Most experiments, we look at the relative efficiency of the detector, where we look at how for every time that I see a gamma ray of that energy, how many times do I see a gamma ray at another energy? For example, in the Coulomb excitation experiments that we do with Prof. Nico, we look at the beam isotope that comes, and we have the isotope in the target. So we look at the ratio of efficiencies between the gamma ray that comes from the projectile or the beam and the target. So once we take the ratio of these two, so this is the same thing as up here for the gamma ray at energy 1, we have the area of the photopeak divided by the intensity, the activity of the source, and the time. And we divide the same quantities for the gamma ray at the second energy. So the activity of the source and the collection time actually cancel out. And we're left with this simple ratio of the areas and the intensities. So this is what we will do today. We won't even bother looking at the activity of the source and the data collection time. So everything is much simpler. And if you look at it, the activity and time are just normalization factor. So if you take this number and you divide everything or multiply everything by the same factor, and then take the ratio of both, that normalization factor doesn't matter anymore. It is gone. So this is a way to simplify things and reduce the possible sources of errors in our analysis. This is what we're going to do. And I give you a code that already does this. Your whole job is to understand what the code does, so you can go in and edit the numbers so that it calculates the efficiency for the data file that you are interested in. Okay. Next, how we find the gamma ray intensity. So this is something that you still need. We don't look at the activity or the time of the collection, but we still need to know how to find the intensity. So here are the two important databases. My favorite, of course, is the first one over here, the yellow one that I have over here. Here it is very minimalistic, very simple. You can search either by radiation. If you have, let's say, in a lab, an unknown gamma ray energy and you want to know where it comes from, you can go into radiation search, look for the gamma ray energy, and it will give you a list of possible isotopes that it's coming from. So you can, it gives you a big list. That's why you have lots of parameters here. What is the uncertainty? And if you want to put a limit on the lifetime or on the masses, you have all of this available here. Today, we are interested in europium-152. So we're actually, when we're looking at an isotope rather than a gamma ray energy, we go here. I'm looking at 152 europium. It gives me the list. So europium actually has two isomers. We put an M at the top here for an isomer, which is a longer lived state. So most states have very, very short lifetime. I'm not sure if Nico talks about this in lectures, but now you know there are some states that are longer lived and we call them isomers. But we'll just look at the radioactive source that we have over here, 152 europium. You have a lot of information, the half-life, separation energies, decay properties. We have different modes of decay. This is what I want to look at right now. So we have different modes of decay. Europium-152 can do a beta minus decay, or it can do an electron capture with a different branching ratio. So 72% of the time, europium-152 will do electron capture, and 28% of the time it will do beta minus. So I'm not very familiar with the nuclear chart or the periodic table. I don't try to remember all of this, of course. So we have the second database that can help us with that, which is the NNDC, the National Nuclear Data Center, and everything is on there. Everything that humanity knows about nuclear and nuclear physics is on there. So you can see list and list of databases for all different types of properties of nuclei. Everything is there. What I want to know right now is for the two types of decays of europium-152, where does it go? So I go straight to the chart of nuclide. In nucleus over here, I'm going to look for 152 europium, say go. And it will look for the nuclide chart. So here at the bottom, it gives me all the information that I found on the other page, of course, and we can zoom in. So let's go to level 2. Here we see europium-152, which is highlighted with the pink border, and all the black boxes, as usual, are the stable isotopes. So we can see that for the same mass number, so for the diagonal line over here of all the masses 152, we have two stable isotopes or very long-lived isotopes that are surrounding europium-152. This is why it is able to decay in two different directions. So when it does beta minus decay, it means it is SM, I believe samarium. 152, no, the opposite. So europium-152 decays beta minus decay, so it goes up to 152 gadolinium, I think. And the electron capture is the opposite direction. It goes down to 152 samarium with those branching ratios. So most of the time it will do electron capture and go to samarium. So I'm showing you this, that you don't have to memorize the nuclide chart or anything. You can always find it right there, and it will come with all the information, the half-lives, everything you want to know is all in one place. So you should be comfortable to use databases and to know where to get the information that you need to know. Here I'm zooming in to level 1 on the nuclide chart. And we're zooming in, we can see all the information right there. So we don't even need to look down. We see the branching ratios, what is the fraction of the time that it does beta decay or electron capture. So those are the decays that we're looking at in the data files today. So if we come back to this this database here, the yellow one, we have the same information over here, and it gives you links to all the other databases. Everything is well linked together, and you can find the information at many different places. What we need to know today is the intensity of the gamma rays. So we need the list of gamma rays from the decay of 152 europium. We have the energy of the gamma rays that are emitted, which is slightly more than the sources we've been looking at in the lab with the sodium iodide. I gamma is the intensity of the gamma ray, and the decay mode over here. So this is sorted by energy and intensity. Most of the time, it is more useful for me to go at the bottom and sort the gamma rays by intensity instead of energy. So I click there, and then they resorted the order of the gamma rays for me, which is more useful most of the time. So here we see that the highest intensity is almost 29%, and the energy of the gamma ray is almost 122 keV. Other gamma rays, 334, 1408, are all the highest intensity gamma rays. So once we look at the data, those are the energy that I expect to be the most intense, the higher counts, the highest peak as well. So even before looking at the data, I have an idea of what I'm hoping to see, what I'm expecting to see. So if I come back to the slides here, we've looked at this, either research by energy of the gamma ray or by isotope to get a full list. And we've looked at how to look at the chart of nuclide. So now you know how to get all the information. Now you need to start working, start doing. So how to fit peaks with Greasy sort. In the lab, we could not nicely fit. We only had the regions of interest. So now we want something a lot more accurate. We will fit the peaks using Greasy sort. So first, I'm bringing you back to the Ubuntu Setup GitHub that we were using for the last practicals. So I have it over here. Zoom is in the way. Okay, Ubuntu Setup. This is the page we were using before, so you have done most of this already. You should have the Ubuntu subsystem running, or you should have a machine in Ubuntu, whatever you managed to sort out last month. You should have root 6 working. And by the way, if you had any issues before, I would recommend that you read again through those instructions, because I kept updating things. So on the WhatsApp group, when you were pointing some difficulties to us and we figured out the solutions, everything is already there. So I would recommend to make sure that I did not already solve your issue. Instructions for Anaconda, Spider, that should already work. And here, before it was optional, and today it is no longer optional. So you need to install the Greasy sort, and that happens on Ubuntu or whatever Linux system that you have. So Greasy sort is based in root. So in root, you can write your own codes and all that. And this is what the gamma ray spectroscopy group at Triumph did. So the group that manages and works with the Griffin Array and the Tigris Array, they wrote this code so that nobody struggles by themselves to sort all the data, since all the data sets rely on the same detectors and the same data format. We have one major code that people have very little to edit. Of course, each data set is different, and we move detectors around, and there's different bugs and challenges in each data set, but the core of the code should be the same. So you need to install that, because there's lots of helpful tools such as the peak fitting that we are going to use today and tomorrow. So if you haven't already, you should install Git. Git works with GitHub. You can easily clone or make a copy or download of a full repository on GitHub, such as this one. And you can also push back any edits that you do on your machines. You can always sync it back to a GitHub repository that you have, so that everything is always safe and in sync. This is how Greasy Sort was built. Greasy Sort is a monster code. It is a huge code that many different postdocs and students participated and contributed to. And the way to make a big collaboration of people work on a single code is by having one copy on GitHub. And then everybody has different forks, different copies of it, and then push back the changes, the edits, to be merged together. So this is really why I'm putting everything on GitHub, because I want you to know what it is and be comfortable with what it can do. And all the codes that we're referring, like Greasy Sort and root and the codes for the COVID-19 mini school that we did, everything is on GitHub because several people are participating into those codes, and it keeps everything in sync. Long story short, you need to install Git. So that's next. You can easily use Git and then clone the GitHub with Greasy Sort. Then you need to go in your bash RC file like you've done in the instructions before. So if any of those instructions don't make sense or not super clear, if you don't remember where your bash RC script is, for example, you can scroll back up and you've already done all of this. So I know for a fact you knew at some point last month how to do this. It is just described above, so I didn't want to describe it here again. You need to add this line into your bash RC script so that every time you open a terminal, it knows where Greasy Sort is. That's the only purpose of this line. And whenever you edit your bash RC, you want to source it again to make sure it's using the latest version. Next step, you go into your Greasy Sort directory and you type make. And this is how you compile a code. This is a big code. So there is actually a make file. I can show that to you actually. So this is my Ubuntu subsystem. And you can see I have two versions of Greasy Sort right now, which is something you can do. You can have two versions of Greasy Sort. I also have two versions of root. You can make them in just different directories with different names, and they can run in parallel. So the latest version is Greasy Sort 4, which is what you are going to install as well. So in this directory, you can see there is a make file. So the make file, we can have a look. The make file gives all the instructions on how to compile this so that you don't have to worry about it. Everything is in there. You don't have to touch anything. It is scary looking. There is a lot of instructions there, and this is why it exists, so that people don't have to worry about it. The only thing you have to do is run make. It is already compiled. So it will only recompile any changes that were done. And here it tells me that the compilation was successful. Woohoo! This is what you're looking for as well. So you will compile all of the files in the different directories. When I say you, I mean the make file. When you type make, it will do everything that is in the make file, and it will tell you, woohoo, this is all you're looking for. So after you type make and you get the woohoo, you're good to go. There are more detailed instructions in the case that you wanted to keep working with Greasy Sort and look at different versions. The wiki on the Greasy Sort GitHub gives you very detailed instructions. If you want to contribute to a code, for example, you have to set things up so that you can push back edits. You don't have to do any of this. We're just using the visual interactive tools to fit our peaks. But this is just to show you how powerful that code is and how you can build codes yourself. That code was built by postdocs and postgraduate students, and also co-op students who come for a term, interns. You call them interns. So anybody is able to contribute to a code using GitHub, and it is feasible with simple instructions here. I'm showing you so that you know it exists, but today you just have to get make and get the yoo-hoo out. Here, maybe you won't need them. This is notes for me that sometimes I need special packages to compile it. I've compiled it on different machines to make sure that you will be able to do it on yours. Let me know if you have any issues, but try this first. This is a five-step recipe to getting Greasy Sort compiled and working. Like the codes that we installed before, I always include a test. And the test here is that all the tests for root should still work. Instead of writing root something, you write Greasy Sort something. Here in my terminal, we are going to look at root FE next. This is the code. Here, I simply did the git clone for the repository, like anything else. And I just want to show you that this is what I showed you in the first track, actually, how to run this. That was one of the code. So root -L, the -L is just to take away the logo. So don't worry about it, -L, and the name of the script. I click enter. It is processing, and it is giving me my efficiency curve. We'll come back to that in a second. What I want to show you is if I changed root for Greasy Sort now and press enter, it is doing the exact same thing because Greasy Sort is based on root. It needs root to function. This is why in our Ubuntu setup, first I had you to install root. You can do a lot of things in root, and now we can do more specialized things using the Greasy Sort code. So once you get your woohoo, you're all set to go. So this you will have to do today or before the practical tomorrow. So again, at 2 p.m. tomorrow, you will work on this. And today you need to take this time to install this. Okay, let's come back to the slides. So we did the first point over here, how to install Greasy Sort. All the instructions are on the GitHub at that link. Now, let's read through this to check that I give you all the instructions. Now, we're looking at 4 arrays. I have a data file for European 152 source data for all of those arrays, and we have 4 groups already. So I would like each one of the groups, A through D, to work on a different array. So you will open the file using Greasy Sort -L and the name of your file. So let's go back again to today's GitHub, which is peak fitting. And like I showed you at the start, we have those 4 files over here. So they're all for the exact same radioactive source from the same nucleus, European 152. And we have one that was collected with Griffin in 2015 for my PhD data. We have one from Miniball, which was collected in 2018 for Kenzo's PhD data. The soccer ball data was collected at Itamba in October 2019 for the masters of Andy Lays and Brendan on nickel 60 and 62. And finally, we have Tigress calibration data that was collected in 2018 again, when the UWC group visited to do Coulomb excitation of strontium 80 and 82. So we have those 4 arrays, and I already have the files in here because I already downloaded everything, of course. So here are the files that are uploaded there. How to open a root file.
Excuse me, Nikita. I want to ask, how did you download those files into your computer?
Yes, very good question. The answer is right here. So to download all the files in this repository, after you install GitHub, you git clone and the address of this GitHub, which is the peak fitting. So once you download this, you will get a directory with your 4 data files and the slides and all the instructions here. So even if you're only going to work on one data file, just use this and you'll download everything at once. It's very small. You can see, no, you can't see the file. It's very small. So just do this line here. All good? Okay, I'll assume that means all good. So we want to open the file. So here, that's what I was going to do. Greasy sort -L, and I will look at my own data. So we realized in the last practical that there's lots of function that I do with my hands on the keyboard that I forgot to mention. So please let us know if there's things that you feel are not working. For example, copy paste is something that I don't think about. It's just muscle memory right now, by now, because I'm just too used of doing it. So to copy this, I highlighted it and did right click on my mouse. And then I do right click again and it pasted it. So to copy paste and do a lot of things that we're just too used to it. So it came up with Prof. Nico as well, where it's just muscle memory. But let us know if there are things that do not seem obvious. Of course, Google will know how to copy paste in a terminal, but we can also help. So here I'm doing Greasy sort -L, and I'm looking at the data for Griffin. So it is the Griffin root file. I press enter. It tells me that it did open the file in Greasy sort, and don't worry about that number. It's not up to date. Now, to see what is in the root file, you type .ls, enter. And you see this is the name of the file. And there is one item in this root file. It is a TH1D. This is a 1D histogram. This is the simplest type of histogram. And this is the same thing we were looking at in the lab with the multi-channel analyzer, just a 1D histogram. So in order to see this histogram, we need to try it. So I'm going to use this name. I don't want to type it, so I highlight it, right click again, and now he copy pasted the name of the histogram. Then we need to do an arrow. So hyphen arrowhead, draw, open, close parentheses. All those instructions are what are in the slides here. So I'm showing it to you to make sure everything is clear. You have all the instructions there, and the video will be uploaded as well. So you will be all set to do everything you need. Once I've done my draw, open, close, I press enter. And it opens what it calls a canvas, a different window where it displays the data. So I'm going to open this wide. This is the European 152 source at the Griffin Array. Here is the name of the histogram, and we have some statistics about the histogram. Entries is the total number of counts in this histogram. And don't worry about the other numbers. We have exactly what we had in the lab. We had the number of counts as a function of energy. So first I want to zoom in where most of the data is here. We see very skinny peaks. So this is what I was saying earlier, the difference between sodium iodine data and the germanium, I hope is obvious. It is very skinny peaks. And when you do detailed beta decay, for example, stop the beam, you want to see very, very detailed. We want to see all the little details and gamma rays, for example, that might be hiding there that were never seen before when detectors were not as powerful, for example. So things that were done a few decades ago, we can redo them now with our high efficiency arrays and maybe see something else. So now I'm going to use the keyboard. I'm pressing S, and it displays a rough energy for all the major peaks that are there. So the most important, the highest peaks, I should say. There's a rough energy. You can see that they're all rounded to 0.5. So they're not accurate energies, but it gives you a good idea of what you're looking at. What is the energy of those gamma rays? So what I can do actually is go back to our database that we already pulled up the energy of those gamma rays and put my spectrum right next to it. And now this is already sorted by intensities. So this should be roughly the peaks that are the highest in this. So first we were looking at 121, and this is what we have. Our highest peak, our highest gamma ray peak, I should say, is 121 over here. What you see here at 39, let me zoom in. To zoom in, I click on the x-axis and I drag and I let go. And then it's zoomed in. So the peaks that we see at lower energies than 121 kV are actually X-rays. Interesting, but that's not what we care about right now. So the highest energy we have is 121. Now I need to zoom out. I will press O, and it zooms out completely. Now I want to zoom in again by click, drag, let go. And now I see my 121. The second most intense is 344, which is the peak that I have here. Third one, 1408, I have here. And you can keep going. So based on this, I'm pretty confident that I'm looking at data from European 152. I hope that makes sense. This is very similar to what we were doing before, except that the sources we used before only had 1 or 2 peaks. Here we have many peaks, which is useful, so we can do an efficiency calibration using many peaks. So this is what the data looks like. What else did I put here? So you know how to look at the list of histogram, draw the histogram, display the rough peak energies, how to zoom in on X and on Y. And then we need to fit the peak. So this is what's next. Let's find a good high, no, let's do a lower one. It's harder at lower energy, so let's show you what it looks like. Our highest energy, oops, it needs to be wide enough for it to zoom in, otherwise he says no. So yeah, I want to show you how to zoom in on Y. So this is the same thing as the x-axis. You click, you drag, and you let go. And you can see that it's zoomed in. To unzoom the Y-axis, you do right-click, unzoom, And now this comes back, but the x-axis stays. To zoom everything out, you click 0. And now the big moment, we want to fit the peak. So you need to follow carefully. I click on one side of the peak. I click on the other side of the peak. And on my keyboard, I press F. And I have fitted the peak. This is what we need you to do. Click, click, F, and you get the information that you need. So the information is printed out to the terminal. So you need both windows over here. So I fitted between those two cursors that I put, and it's giving me all the information. So the cursors I put at channels 97 and 149. So this is the name of this gate over here. The centroid, based on this fit that he's done, he says that it is at 122.18 kV with a very small uncertainty. So here we need to have a good discussion on what code can do and what physicists can do. So brute and Greasy sort are just codes. So they're using maths and numbers, and it's giving you a ridiculously small uncertainty here because he doesn't know about uncertainties. He doesn't know the physics behind this. So of course, all the spectra that I'm giving you today, the 4 spectrum, are already have an energy calibration. So unlike what we were doing in the lab, we were using channel numbers, and we didn't know exactly where we needed to find a conversion factor between energy and channel number. So here I've already done that for you so that you can worry about the efficiency calibration. My point here is that there is always an uncertainty on the energy calibration. So you should have noticed that in the last 2 pracs in the lab. And here this doesn't know about this uncertainty on the calibration. So this is purely a mathematical and statistical uncertainty, and we don't consider it. The uncertainty on your calibration would always be bigger than the uncertainty from your fit over here. So the energy, this is what we were looking at in the last lab, and this is how easy it is to get it with a full gamma ray spectroscopy code. And let's come back to the fit for a second. You can see that this is not a Gaussian. This is not a simple Gaussian. This is more complicated than that. So we have something that kind of resembles a Gaussian. However, it is not symmetric. It is the sum of two of a Gaussian with a larger side over here, and there is a step. So the black line that you see here is the fit of the background, what he thinks is the best fit for the background. So that is where all the magic comes in. This is where you need to use your physicist brain to say if that makes sense or not. So my point is, this is not a simple Gaussian. This is high-tech, advanced, and this is when zooming in on the y-axis comes useful. So I want to zoom in on this to see how well the black line fits with the data. And you can see that it's not, on the right side, it's not that bad. It's kind of averaging on the background here. However, here you can see that the red line doesn't follow the data, and the background is a little bit higher than I would like, that it could be closer to this. So there is some work to do on the background fit. Here I do right click on zoom, and I want to look at the top of the peak. So if you can see here, the 2 data points, the highest data points for that peak, you have one here and one here. However, the fit, his best fit, goes much higher than that. So it's overshooting on where the data is actually, where the points actually are. So this is not the best fit that we can do. And you have to play. This is where you have to play how to get the best fit. So I want to, oh, Nico, you raise your hand?
Yeah, actually, I one curiosity. So this left shoulder is because of, generally is because of neutron damage. But for the Griffin detectors, you don't have any neutron damage because it's mostly used for beta decay. So do we know why you have this left shoulder, left peak, or I mean left trend on the peak?
This,
I mean, I know.
This can definitely be neutron damage. The Griffin Array is right on top of the target stations. And a study of background is something that I worked on too during my time there. So we have that. And also it can depend on the energy calibration. So what I did not mention is I'm giving you one histogram per array. So for example, this Griffin histogram over here is the sum of the 64 crystal of the array. If even just one of them is not perfectly calibrated, when you add up all the 64 histograms, that will widen your peak. So that can explain why there's a left shoulder.
Thank you, Nikita. That was more a technical question, but it was curious to see why, if you don't run neutrons there, why you have this. Well, you say there are some neutrons going on.
We have a lot of things going on in this area, yes.
All right, thank you.
Yeah, no problem. So I think it's good also for the students to hear about technical questions. So I'm trying to make it here not scary and basic, so that you get your feet wet, that you get into it. But of course, like you do full degrees on this. This can be a master's or a PhD, and it takes years to do this perfectly. Or we never even reach perfection, but to do as best as we can. So this is not what I'm expecting this week. Like, I want you to get in there and play a little bit with fitting peaks, and just be aware that this is what we do. This is real physics. This is data coming from real germanium arrays, and people study that for years. But I just want you to get in there and to see how it is in the simple world, but it can get very complicated. So here, I'm not super happy with this fit. And like I said before I did it, at lower energy, we have the most background, and the peaks will have more distorted shapes. When you fit peaks at higher energy, it will be much nicer. So here I'm showing you the worst case, which is the 121 keV. I want to redo this fit. I'm going to press N. Everything disappears. The cursors and the previous fit disappears. And I'm going to do a slightly narrower gate to see if that helps with my background. So I click, I press F. He's working hard. He didn't like that. Will it? Okay, so I defreeze it. That was my first peak. This is my second. So now we can compare the different values. So first, just looking at the centroid, it did change a little bit, but just the small decimals. So this is not a big change. The next values that we have is what we're interested in. So we want the area, which is the number of counts in the peaks. And we have two values in order to get that number. There's two values that we can look at. There's the area and the sum. So those are the numbers for the first fit that I did. And this is the new one, where you can see the boundaries are a little bit narrower than the first one. So the area, the number that it gives you here, is the fitted number of peaks. It is all the number of counts that are under the red curve above the black one. So we know that this number in red, the area, the fitted area, will be higher than the actual number of counts. Just by looking at the top, we saw that we overshoot the number of counts. And this is what we see. The area number is already a little bit smaller than the sum in both cases. So the difference, I meant to say, between the area, which is the fitted, all the number of counts under the red line, while the sum number is just the numbers on top of the background. So it doesn't shoot up over there. And if we zoom in here, this follows much better already the data over here. And it only counts the numbers where the data actually is on top of this background. This reduces the uncertainty on our number of counts by sometimes a lot. When the peak is not very good, we tend to overshoot, or we cut out like before it was cutting out a lot of data. This uncertainty will be only in the area. In the sum number, the only uncertainty comes from where the background is fitted. So I hope this makes a little bit of sense. You'll get a feeling when you play with it, but the thing to know is the sum will always be bigger. Forget what I said. The sum will always follow the data, not the fitted lines. So depending on if it's cutting or overshooting, it might be bigger or smaller. Don't worry about what I said. You'll get a feeling and you can tell me I'm wrong. So I want to zoom out. Let's look at another peak. I'm going to do N to remove the cursors, O to zoom out, S to display the energy. And now I want to look at a better peak. So 1408 is also from European 152. It is one of the strongest, and you will use that in your efficiency curve. So I zoomed in around it, click, click, fit. It's not very happy with my fits. I need to, so when it gets stuck, I just did a quick Control-C, and then it gave me the value. So here we have a higher energy peak. We see that the background is much lower. Actually, we don't really see the background with this scale. I'm going to press L with my cursor on the canvas, of course. Now I press L and it changes the y-axis from linear to log. So I can see actually where the background is. And you can see that this fit for the background is not very good because I placed my cursor right on top of another small peak over there. So that was not good. So I'm going to do it closer. I'm going to press L to come back in linear and to remove my cursors and do click, click, F. And now I get another fit. Again, in your terminal, it collects all the values for the different fits that you do. So you can do several fits and still look at the numbers and see if it agrees or not. So the first fit that we did, we saw here that there was a little bit of a difference between the area and the sum, which if we have a perfect fit, there shouldn't be a difference. So if you look here, the values are very, very close. So this fit looks much better. So we can do L again. So I'll click on the canvas, click L, and it's still not good. It's still very high, but by playing with the boundaries, you have to find the best fit that you can. Of course, the peak fitting can may be made much more advanced and change the parameters of the Gaussian and the step of the background very carefully. You don't have to worry about that today. So what I want you to submit is a screenshot of your peaks, exactly like what I'm doing. So if you think this is the best fit, I want you to take a screenshot and put all your screenshots together with your code and your fitted efficiency curve. So what are we missing for today? So I give you all those instructions. They're also written down. To close a root or Greasy sort, you go to your terminal here. I just pressed enter to get back the command line. I press .q and I'm out. So you're not stuck in a file. What I want you to do is save screenshots of your fitted peaks and the number of counts, and always the sum, because the sum includes less uncertainties because you're not actually following the fit, just the fitted background. More tools are available on the Greasy sort wiki, which has very good documentation. So here, this is the page for the interactive analysis, and you can see a bunch of commands. So I already showed you the ones that I use all the time. For example, O to unzoom the entire histogram, and there's different fitting functions. So the ones that I've been using is just F, not capital F, to do a fit, which is a skewed Gauss with an automatic background with the minimum output. You could want to do a simple Gaussian, but we can do much better than that, but it is also there. And you have a lot of things to go through if you want to look more into this. But I already wrote clear instructions of all the functions, all the comments that I've used right now, so the ones that I used the most commonly. And just to finish today, so now you know how to fit your peaks, how to save screenshots, I assume, and save the area of your peaks. The next is to look at the root efficiency code. So just like the other repositories, you download with git clone, and it will make a root FE directory in your Ubuntu system. Download the data files by cloning the GitHub that is peak fitting for this prac. Next, we open actually the code, the root efficiency in gedit, and we edit it with the peak areas and the uncertainties obtained from your data file where you fitted everything. And here I'm letting you know, when you edit the script, you should save it and close root or Greasy sort to run it again, just so you don't get stuck. So here I'm going to show you my root FE directory. So you get the code and the README file, which is all the instructions that you see on the root FE here. So all those instructions come as the README file. So you always have a copy. You can add notes if you figured out some things, you had issues, you can have this there. So gedit root FE, which is the code that we looked at in the first prac and at the beginning of this prac today. This does everything you need. I put a lot of comments in there that explains to you every single line of the code. So I am not going to read it with you. This is your job to go through the lines, the explanations that I already wrote, and I want you to tell me what is not clear. So anything that doesn't make sense, that doesn't have enough explanation, then you need to tell me so I can fix this. So you have to look through this. There are instructions there and on the GitHub how to run it. I've already showed you Greasy sort or root -l root fe.c. This code does absolute efficiency and relative efficiency, but today we don't care about the absolute. So the first part where it does absolute, you can totally disregard. So the code already got easier for you. This is all commented out, it doesn't matter. The part that you have to actually work is over here. This is the list of gamma rays, energy, intensity, intensity uncertainty, area, area uncertainty, and the number of decays, which you don't have to worry about for the relative efficiency for Europium 152. So I already put the in the energy of the gamma rays, the intensity, and the intensity uncertainty from the database here. Do not trust me, verify those numbers, and then tell me that I did a mistake. So the first 3 columns are already set. What you have to do is copy and paste the areas, the summed areas that you got from your data files. Edit them, put them in there, try to fit as many peaks as possible. So here for the data file that I was looking, some peaks were too small, so I just commented out. But the more peaks you add into your curve, of course, the better the result will be. This is what I want you to do tomorrow. So today you should install Greasy Search. It is 5 steps, 5 lines that you copy paste from the GitHub. Let me know if that doesn't work, if anything happens. And tomorrow I will be on Zoom and you can ask me any questions you have. You can share your screen to debug if Greasy Sort is not working, if root FE is not working, and you need to tell me what is not clear in this so that I can make it clear for you and everybody else. So this code, you know it's running. You just have to read the instructions. I tell you what each line does. So I need you to read this. And then just one last time, how we run root FE, Greasy Sort -L, root FE, enter. And it comes out using the numbers that you put in the script. So I want to see your fitted peaks. I want to see this curve, and I want to see your edited root FE, where you kept all your areas. That is it for me for today.
Excellent. Thank you so much, Nikita. So you don't need to compile anything, no? If you change, obviously you have to exit, as you mentioned just before. Exit the program with .q and change whatever in the gedit, in your editor, whatever you want to change. If you miss, if you didn't put the right areas or the right energies, you change. You just edit the right numbers, and then again, run it as Nikita just showed.
Yes. So a small tip that Nico already mentioned: if you put the %, at the end of a comment, you keep control over the terminal. So when you work on a script that you want to rerun several times, what I do is I open it and keeping control of the terminal. So I have my code over here that I do changes to, I save it, and then I can run it here.
Right.
And then I see what the changes did. Then I close this and rerun it again every time I save this.
Right. And you can go with the up arrow, as you also show, right? With the up arrow to see what you have done before.
Yeah,
so you
exactly.
have to remember all these commands. So another question that we have here from Shoki is that when is this due? Nikita, I want to let you know that this what Nikita is showing you is a common practice in any research institution. You go to any laboratory, either in astronomy, you also have to do an efficiency. Anywhere where you have a detection system, you need to do an efficiency calibration of your system, your detectors. And this is very important for us because even the light of a star, we have the high resolution spectrograph at SALT in the South African Large Telescope. So there you have a blue arm and a red arm, right? So you need to always calibrate these 2 arms because otherwise your spectrum doesn't look good. Everything is, there's a mismatch and you don't really know what are the lines, and that's energy calibration. But also you need to know efficiency calibration, because sometimes it's important to relate one peak to the other, right? And if you don't have an efficiency calibration, because one peak, the system will detect it more than the other. So this has to be taken into account when you relate one peak to the other. This is the case, for instance, when you do abundances ratios and you want to know what are the nuclear reactions involved in explosions, in stellar explosions, how elements are created in the universe. And all these lines must be corrected for an efficiency. So it's not only in nuclear physics, but basically in every field. So Nikita, thank you so much. And tomorrow there's another session. But how long do you think they can play with this until next week?
Yeah, I would give a week.
Yeah.
The week that this is not we don't ask for a full report. I'm just asking for one file with your screenshots for at least 8 peaks.
Right.
So in the code there's more than 15, but 8 peaks, the bigger ones.
How do we make sure that each one is unique from the students?
Any fit is never the same. So by submitting your your edited scripts, we will see the area is different.
And also every area will be different because you're going to do it as independently. So yes, I will say to send us the code as well, right? Not only right.
Yes, so I put that in the slides here. Mm-hmm. Please, in one file, put screenshots of all your peaks. So that should be 8 little screenshots or more. Yeah. Your edited root script, which is just a few lines to edit, and your screenshot of your efficiency curve.
Perfect. That's a beautiful practice. So guys, now you are closer to do research.
This is very close. This is research. This is what everybody does. This is the first step on every data set analysis. So this is very good practice. And the goal of doing this is get you to play with all those tools. So with this, you're getting familiar with root, with a state-of-the-art analysis code. You're playing with germanium detectors, so a different type of detector. And you're using GitHub, you're using Ubuntu, you're using a lot of things. So even if what we are asking you to do, the task doesn't seem that complicated, it involves many things, different components that you have to be comfortable with. And this is just the first step of what research is actually. So we do this, but just even fitting the peak can be made a lot more advanced. So the sooner you get comfortable or just in contact, so I won't say comfortable, but just that you've heard about this technique, when you continue doing research, you'll already have an idea of what actually it means. So I think that is a big step. And also how to look in databases, like there's a lot in this prac. But all I want to see is a few screenshots. And here, this is
any questions, Nikita? Ask for questions if there's any questions before we go.
So yeah, just one last point. I want to show that on the GitHub and the README file, I included links to publications for the 4 different arrays, so you can have more information on the detectors. So I give you a quick introduction and a configuration of each of the arrays that we are using, but those are actually published. So there are links that you need to use the UWC VPN or be on campus to be able to download, like myself. I am connected right now, so I can have access to it. So for Griffin mini ball, the soccer ball is using detectors from the Aphrodite array, which was also published. So it is common practice to publish a nuclear instrument and methods in physics research paper, a NIM paper, for any new array, so that all the physics papers related to this array always refer to there. So all the details on the detectors are in this paper. And you have a paper for each array. So the last thing, we have 4 groups and we have 4 arrays. So I would suggest that the group A works with the Griffin data, group B, mini ball, C with soccer ball, and D with Tigress. Just so that not everybody works with this. If you have a very strong feeling about working with one array in particular, you are more than welcome to. But there's a little surprise in each of those data files. So this is real data from real arrays. Nothing is the same. Everything is different. The collection time for each of those run is different. The number of crystals is different. So everybody gets to have fun with each of the data files. Any questions before I see you tomorrow? So I can't see the chat window. Okay. So I would expect everybody to work on installing Greasy sort for tomorrow, so that you can work during the prac on making your peaks. So I can help you with that rather than compiling. So the WhatsApp group is there, and we're meeting tomorrow at 2.
Thank you, Nikita. Thank you so much for the nice prac.
You're welcome.
Okay. If there's nothing
from anyone.
Tomorrow, I expect lots of questions, because today, as Nikita says, we have condensed lots of information, and it's impossible. Many hours of work by many people. I don't think you can assimilate so much in such a short time.
Yeah. So I gave an introduction on everything, but we're not expecting a full report, and there's no exam on this. So that was really just for fun of getting a taste of the different types of detectors that we use, the different type of analysis that we use. So there's no pressure on this. It's really just to have fun and look at everything. The parts that I actually want you to do tomorrow are well defined point by point in the slides. So there's no pressure for anyone. It's just fun playing around with new data. Okay. No,
Yep.
Nothing. Okay, we just need to download that step 5 GitHub. I'm not really sure. Okay, we have a question about what is due today. The only thing that I expect from you before 2 p.m. tomorrow is to install Greasy sort. So in the, yes, this step 1 to 5 of the Ubuntu setup. This is the same page that we had before. You've already done all of this last month. We just need to do the very last step, how to install Greasy sort. So that is 5 lines that you have to copy and paste in your system.
So Nikita, where are the publications that you mentioned before? In which? In
the peak fitting.
In the peak fitting, okay. I see. There we go.
And yes, so here also in the peak fitting, I sent you to the instructions to install Greasy sort. So you have all the information in one place.
Mm-hmm. So it's not the soccer ball, it's the Aphrodite, the old Aphrodite array, right? Because the soccer ball is a different setup. I just checked I didn't know that there was a publication for the soccer ball.
It's not for soccer ball, it's for the Aphrodite detectors.
Yeah, right.
It's just the frame that was used was
different. So yeah. Okay. There are some more questions.
Okay, so was that clear? The only thing I just want you to install Greasy Search. So it's those 5 lines.
Mm-hmm.
And then you get the woohoo and you're good until tomorrow, where we get to play.
Okay.
Okay. You know how to reach me, and I will see you tomorrow.
Thank you. Bye, Nikita.
Okay. Bye-bye.
Bye-bye.